Okay, everybody. What I'm showing here is a video game, and instead of me playing the game, you're watching a machine play the game using machine learning. And so let me spend the next few minutes telling you about that. And as I talk, you can watch the machine play and judge for yourself how it's doing. The number on the right up here is the score, top right. So when I play the game as a lowly human, typically I can get between 1 and 200 points without too much trouble. So ideally the computer could get that sort of performance. When you get shot, the game is over, and here it'll reset the score back to 0. Sometimes I'm watching this and the computer just gets shot. You're like, what the hell are you doing? It would be so easy to avoid that. And I really couldn't tell you why it sometimes doesn't do as well as one might hope. Okay, so this is called a space shooter game, and I wrote the game based on a course that I took in Udemy, and it's written in Unity, which is a game engine, and that's designed to enable you to easily make games. So I took this game, which is written in Unity, and recently they came out with a machine learning component to Unity called MLAgents. So you can take this MLAgents and make your game into a machine learning game. So basically at the core of this is a neural network. The data from the scene is getting passed into the neural network, and then the neural network makes a decision and passes it back to the player. The neural network is done using TensorFlow, which isn't part of Unity in this example. So it's sort of running two programs simultaneously. It's running this Unity video game. It's passing the data out to TensorFlow, which is, I guess, running in Python or whatever, and then it passes the data back into Unity. So that's the way that works. What else can I say? I modified the game a little bit. What you can see is that there's a bad alien that appears directly above the player and drops a bomb. And the reason I did that is because otherwise the player just tend to sit in the corner and fire, and he did pretty well. So every once in a while you'll see this vertical enemy come out, and that's to force the player to move around a little. Right now you'll see the game is paused, and what it's doing now is it's actually training. So I'm showing you the game in a training mode, and so the way this works is that it'll play the game for a few minutes, and then as it plays, it's saving all that data, and then at the end of the few minutes it'll take all that data and train it, try to improve it, and then keep playing. So I've actually had this running for several days, and hopefully on each one the performance improves. Sometimes you'll train it and the performance will actually get worse. That's like learning, because sometimes when you're learning to do a new thing, you actually get worse at doing that thing before you get better, and that certainly happens here, and I'll show you some data to back that up. The machine learning methodology is called reinforcement learning, and that's different than typical neural network learning. In typical network learning, you have a set of data and you're trying to solve something like linear regression or some problem. But in this case, reinforcement learning is different because the actions of the player will impact the game, and so you can't train in that simple way where you have a data set and you're trying to train to the data set. You have to consider how the actions of the player affected the result. And this is reinforcement learning. The algorithm that's used here is called actor critic. So the actor is making a choice to make some action, and then you also have a separate network that's the critic that estimates how well it thinks the action is going to do, and the critic feeds this information to the actor, and both of these actor critics are trying to improve their performance. I won't explain that in detail, partly because I don't know that much about it. But it's supposed to be a very powerful algorithm, and supposed to be better than genetic algorithm. I've often seen genetic algorithms used, and maybe they would have done better. I didn't really directly compare, but this is supposed to be more powerful. So I'll just tell you how I judge the performance. I'm sort of watching this, and sometimes it does well, but right there it took a bullet, if you saw it, and you're like, why didn't you move out of the way, you stupid friggin'? But there it did move out of the way. Especially on the right side, I find it doesn't move away from a bullet as much as I think it should. And I think what's happening is it's trying to avoid the bullet by moving right, and it doesn't do that because it can't move right at the edge of the screen. Something like that. But ideally it would learn that it's at the edge of the screen, and in that case it can't move right. So I don't know what to tell you there. When you feed the data, what I've done is I've taken a set of features from the screen. So this is the location of all the aliens. It's the location of the player. It's the location of the player bullets. And it's the location of the enemy bullets. So there's like 50 some odd pieces of data that represent each point in time. And this data is all fed into the computer. And the neural network is a 3-layer network. It's a traditional fully connected convolutional network with 512 nodes per layer. So 3 layers, 512 nodes, fully connected layers. That's a fairly small network. The thing is, as you make these networks larger, they're harder and harder to train. They take longer because you're getting a limited amount of data from each experiment, and you have millions of nodes. So there's sort of a dimensionality problem here. You would think, well, I'll just make the network larger and I'll get better performance. That's not really true, because it'll just take longer and longer to train. And if something takes like a year to train, maybe it would be better performance, but it's not really useful. I mentioned that this takes several days to train, so I've just been letting the computer sit here play video games for several days. And I've stopped now and shown you this video. I could wait another couple of days, but eventually I got to stop somewhere, right? Maybe it would be better if I used a GPU or a more powerful computer, certainly. I tried using cloud computing, but it didn't work out too well in this case, because the cloud computer wasn't really configured to play Unity. So, and additionally, this setup isn't apparently configured for a GPU computer. So let's just watch a little more. You can skip ahead if this is boring, but might as well watch more, especially since it took me several days to train it. Looks like we're having kind of a good run here. Like every once in a while you get a really good run. So that's 147 points, which is pretty good. Okay. And now we're back to 0. So every time it gets killed, it goes back to 0 and starts playing again. It just keeps playing and playing and playing. I think honestly I could have written, I haven't done this, but if I wrote a simple algorithm myself that said, if there's a bullet above you, move left, or if there's a player there, move right, I'm pretty sure that I could do a lot better than this. Because sometimes it just, or even if I took this, maybe this is good. If I put a thing in there saying, just don't run into bullets, So you can tell, this is not a bad result, but it's not as good as one might hope. Kind of mixed. It is kind of fun to watch it, actually. It's kind of addictive. In a few minutes, I'll show you some more technical details about how I set it up. But let's just watch a little more. Oh, now that's a pretty high score there. Oops, got killed. So maybe if we give this another month, it would be great. I really don't know. Okay, that's enough fun. I think you got the hang of it. Let me just show you some more details. Here's this is Unity MLAgents. That's where you can it's a GitHub page. So this is where you can download this type of machine learning. This is just a shout out to this Udemy course I took. It's by Ben Tristan, this guy. So it's called Complete Unity Developer. So if you want to do this thing, you really have to know some programming in Udemy. And Udemy is a good way to learn it. This is kind of fun. This is a chart. So if you use TensorFlow, you have these tensor board. This is the way you can monitor the data. So what this shows is actually over several days, it's a plot showing the performance of this algorithm. So what you can see is actually over here it was higher than it is now, and then it drops a little, and then it goes back, and it kind of varies, like quite rapidly even. Like here it was doing pretty well, and then boom, it dropped to pretty poor performance, and now we're over here, and so this is constantly training and updating, and you can see it kind of has a general tilt upwards. So, maybe if we wait another couple of days, it'll be a lot better. That's certainly possible. But, after a while, you just got to give it up, right? So that's that. And going back to the game here in Unity, what you can see here is this is a command window. So over here, this window is sort of controlling Unity. It's running the game, and it's recording the result, and it's running the machine learning. So right now we have another machine learning. And that's what's kind of fun about this. Like as it trains, you're always saying, well, let's see if this guy is any better than the last guy. and sometimes it is and sometimes it ain't. So it can be a little addictive to watch. You know, at 2 a.m. you can wake up and say, how's the video game go? Okay, and the way this is programmed is over here. Let's see if you can see this. So this is Unity, and these are different objects in Unity, and most of this is just a standard game, but this is something called a player here, and what I've done is I've added an agent, and that's how it learns. It has a brain, and what you can see here is all the data that it's sending out. It's sending out the current enemy positions, up to 5 enemies, and it's sending out where the enemy was last. So using this sort of data, the program could track the enemy. It's not recursive, so you only get this sort of data every time. You don't get any previous data. The program only makes decisions based on what it sees now. This says, is the enemy active? So over here, like, there is no enemy 3. There's up to 5 enemies in the scene. This says there's only 2-player lasers allowed at a time. I've sort of restricted it so the player can only fire 2 lasers, because otherwise you just fire a lot of lasers and the game isn't challenging. And this says there's 6 enemy lasers. So here's 6 enemy lasers, all their positions, and then here's the prior positions. Actually, I don't send all of this data. What I decided is that I wanted to reduce the amount of data to possibly improve the performance. So I don't send this data as to whether the enemy is active or not, but I just set -1 if there's no enemy there. So right now there's only 3 enemies on the screen, or 4 enemies, or 4 enemies. So it always sends this list of 5 elements. You have to send the list in the same way. So it sends a list of 5 elements, and hopefully the program can figure out if it's a -1, then just ignore that element. But otherwise, that's important. So it doesn't send this data, is enemy active. And it does send this, current enemy positions. And it does send this, the current X position and the current Y position. I don't know why it sends the current Y position, because I always leave it the same. And what you're seeing here under movement is the decision that the program is making. You can see at any given time what it decides to do. At any given time it gets a reward. So if it shoots someone, you give it a little reward. Or if it dies, you give it a negative reward. And it's these rewards that are critical to machine learning. So it's like, oh, good job, here's a lollipop, or bad job, here's a kick in the pants. And hopefully by just like a dog, I don't know, you might train a dog by giving it a reward or a piece of a little treat, or if it does something wrong, you might, say bad dog. And that's sort of the way this reinforcement learning works. And one thing that I found is it's pretty easy to make mistakes in designing your system. So, let's say you screw up your reward a little. Let's say you give it 0.1 and you shouldn't. Then it'll screw everything up. Or let's say you give it a piece of data that's somehow the wrong piece of data. It can be hard to debug it and understand that you're giving it the wrong data. It's not obvious. But if you do that, you'll get a bad result. So that's one challenging aspect. You have to write everything absolutely correctly, or else, garbage in, garbage out, that sort of thing. And even if you do write it correctly, you can still get a bad result. I mean, let's say you give it a reward of, 0.3 for killing an alien, but only a reward of minus 0.1 for dying. It might choose to kill the alien and then kill itself, which isn't what you want necessarily. So you have to be smart in understanding how your rewards can yield a result. Okay, well that's my story, and I hope you enjoyed it. And if you like it, let me know. I'll just let it play through this last game before I stop. Pretty good score here. I was saying 200 is certainly good. So I don't know if it's this lot. Every once in a while you get a really good score. That's it. Okay, thanks everybody.